All right, today I'm going to talk about a very illuminating concept, Nightgaunt, Opto-electric propulsion for relativistic microcraft. And if you understood any of those words, I applaud you. If not, we'll go right into it. So this is a very out there concept, quite literally. So let's dive into it. Now, the problem, the background, this is a series of things I'm going to be doing for a proposal pitch for the NSF in the not too distant future. But overall, the integral concept is that of a solar sail, a idea like the Star Wisp proposed in the 80s and recently demonstrated with the Breakthrough Starshot project using a laser to propel a spacecraft. So, relativistic spacecraft may require external power transmission or bulky internal power. For example, a giant laser to push things that is in orbit around the sun, or an onboard thruster with lots of fuel, whether it's chemical rockets, fusion, whatever, ion drive. But if you could have completely propellantless propulsion, that opens a lot of interesting doors. Now, graphene energy harvesting is where this gets really interesting. This and optical sails may provide an alternative, both in space and down here on Earth. So, how's it work? As I mentioned earlier, Star Wisp was one of the more famous examples of a beamed power craft proposed decades ago. There's also Starshot, funded by Breakthrough, all the billionaire crowd, basically. But Starshot uses a device with bulky RTG, essentially radiothermal isotope generator, kind of like what they used for the old Cold War space missions. Something that gradually wears down and it's limited by the half-life and it only has single-digit efficiency. Basically hot rocks with a thermocouple. Hundreds of kilograms, so it rules out relativistic acceleration on a realistic time scale. But how do we get something up to that speed and make it practical? Now, moving on to the quantum realm, graphene energy harvesting converts the Brownian motion into electrical power. Simpler terms, Richard Feynman once thought that the random motion, the Brownian motion of molecules, because molecules superimpose, they drift around all the time, that's their random Brownian motion, could not be used to generate meaningful electrical power. Just last year, a researcher at University of Arkansas disproved this by having a vibrating graphene membrane in between two capacitor plates that was able to generate a good amount of electrical energy. So, it's not quite free energy, but it's something that's effectively close enough. Now, there also is optical modulation technology, ability to combine smaller beams into a larger one through polarizers and such like that. So the idea here is get a bunch of small lasers powered by this Brownian motion system into powering lasers that are focused into one thing and focused on a small point. Instead of one big laser and one giant sail, do the reverse. Focus a lot of smaller things on one particular really, really small point to get things going. This is where we get the micro in the microcraft. So, in short, the green block in this cartoon is where the graphene circuit would be, powering lasers going through optical filters and modulation systems, all focused on one mirror. And essentially, that would be reflected. And for additional energy scavenging, you use photovoltaics to get any energetic photons that come out. Basically, we're treating it like a rocket, but the exhaust is coming out at the speed of light because it's photons. The mirror and the laser can be adjusted if you want to change trajectory. Photons don't have mass, but they have momentum. We don't violate conservation of momentum because the photons are still providing that. Now, to test it out, without going too much into the details, because this is still an area of potential intellectual property for a company, fabricate the graphene energy harvesting and laser MEMS, test the thrust generated, optimize and iterate here on Earth, because it also has applications in medical technology for things like imaging or implanted medical devices like artificial hearts and cardiac pumps. So, low mass and low cost. You could make relativistic craft or deep spacecraft more accessible. You could do for deep space what CubeSat did for low Earth orbit. So, potentially, based on some calculations I've done, interstellar round trips to Centauri in a decade or less. So, low mass and low cost craft with internal power supply, not needing all that icky radioactive stuff, large photovoltaics, or a big laser pusher. It has really cool implications. So, any questions? I'll see you in Alpha Centauri otherwise. Stop the
Great.
recording.
Yeah,
Questions?
let me stop that.